Thanks for the great introduction, and thank you for having me. So, my name is Marjan, and I'm lead DevOps engineer at Zulke. So if you're wondering, we have our booth at the first floor, so feel free to visit us. And I'm working as a DevOps for around 10 years now, working with Kubernetes for sort of 5 years. I'm a certified Kubernetes administrator, and I'm passionate about two things. First is rock climbing, and the second one is digital sustainability, which I will talk about here in the context of Kubernetes. So, moving on, what are we going to talk about here? We're going to cover some basics. Then we'll dive quickly into some measurement things, how to measure actual emissions, then steps to reduce, and last but not least, summary, and if we have still time, I have a timer here, so it's a bit pressure. So we'll dive into some Q&As. So starting with the basics, we will first speak about basic terms, how the IT infrastructure emissions look like, what are actual cloud provider emissions, and in the end, Kubernetes cluster emissions. So starting from the basics, basic terms, we hear about a lot, global warming, what it is, and it's an ongoing increase of Earth average temperature that is caused by us, by human activities, unfortunately. We have next the everlasting greenhouse effect, and it's the primary cause of global warming, unfortunately, and it describes the emissions of gases that trap heat, carbon dioxide, methane, and nitrous oxide. Next up, we have another term, carbon, and this term uses or often derives all of the greenhouse gases. And why carbon? Because it's the most present one in the atmosphere, up to 76% of total greenhouse gases emissions. Sustainability, it's a quite big term, and it's society's ability to exist and develop without any depleting of natural resources and saving our future. And renewables, you might have heard about it, but renewables are renewable sources of energy, and those are the natural sources that get replenished over time, such as wind, solar, geothermal energy, and biomass. Moving on, IT infrastructure emissions can be divided in two ways. First of all, we have on one side embedded carbon or embodied carbon, and we have emissions, operational emissions. On one side, embedded emissions are emissions during the production of and the delivery of the hardware, and it's quite intensive and quite hard to measure them, and they really rely on hardware supplier data. And this data, you guessed it, it's often not available, so you need to evaluate the data, or maybe, finger estimate it, whatnot. And the second step are the operational emissions during the operation of the hardware. And mostly, it goes through power consumption. So this will be our driving force here and in this talk. Different energy sources have different carbon intensity. What does that mean? That means that each energy source emits additional or specific amount of carbon in the atmosphere, and based on the source what is used, we're calling that carbon intensity. And it's measured in grams of carbon equivalent gases, so grams of greenhouse gases per kilowatt hour. In the next slide, you will see how much, for example, hard coal, which is pulverized, it emits, I'm not sure if you see it well, but it emits around 1,000 grams of CO2 per kilowatt hour. So that's quite much. But wait, okay, somebody may ask, okay, we are running everything on cloud. Are we actually don't need to care about it? Are we running on renewable sources? Well, yes and no, because every cloud provider is environmentally responsible on their own way. What does that mean? Basically, cloud providers report emissions, but almost everywhere they either don't provide them in a functional way or always misrepresent them. They often focus on market-based emissions, where the electricity is bought from instead of produced, and this is really another story to dive into. Sometimes they're not including location-based emissions, which we actually want to know about. And last but not the least, they are often coarse-grained. What does that mean? Basically, reporting is either done yearly or a half-year or monthly basis, and we really want the data to be more granular. So next up, emissions from Kubernetes clusters. So here we have power consumption as the main driver, and that means more energy consumed, often more carbon emissions. And we can look at the pods like air in the balloon. If too much of pods in the Kubernetes cluster, this balloon will burst. And that's why we're going to focus on two things. First, reducing emissions by optimizing workloads inside the cluster. And next, we will look quickly on reducing emissions by optimizing outside the cluster. Here, our focus will be inside first, because with looking into the insides, we make sure that the outside doesn't go out of control. But before we start this, we'll quickly dive into a couple of tools that we use to measure emissions in Kubernetes clusters. One of them is Kepler, or Kubernetes Efficient Power Level Exporter. And I've got this. OK. So this is a tool that is used as a Prometheus exporter. I'm not sure if you know about it, but in a nutshell, it collects the data, then it aggregates it, optionally does the modeling, and then presents the data. There is going to be a talk today about Kepler, a bit deep dive. This is just a run through the tool itself, so feel free to check it out. This is how Grafana dashboard with Kepler data looks alike. So if you see there are some carbon emissions at the top left, you can see how much those emissions, what are the numbers for those emissions across the namespaces or across some pod within the namespace. And this is some demo dummy dashboard that I've created. Next tool that we can use is Scaphandr, and this tool is actually energy consumption metrology agent. It's something similar to Kepler, but it relies on a different approach. It takes the data from the host, so CPU, memory, GPU, I/O, and sensors take that data, especially this from this PowerCap RAPL, which is a feature of the CPUs, and then this data is made available for the exporter, and the last component is the exporter that takes that data and makes them available to standard output, to Prometheus or whatnot, and then we have this presentation layer, which is again Grafana, and this is an example of Grafana dashboard that you can see for Scaphandr. And as you can see, for example, this host power consumption, it's around 15 watts. And you can see a lot of the different numbers. You can see the process, top consumers, and whatnot. So quite good tool to monitor your power consumption. So moving on, while we all here, talking about the steps to reduce emissions inside the cluster. So we'll start with the most basic ones, set resource requests and limits. Why? Because workloads run unprovisioned in the cluster. So by default, one pod can probably destroy the whole cluster if left unhandled. How can we do that? So to set these resource requests, we mainly reduce the power consumption of workloads. We use less instead of possibly all. We do not overconsume resources, and last but not least, we are able to plan ahead. And one of the side effects of adding the resource requests and limits is basically improving scheduling, stability, and quality of service. So scheduler can make better decisions for us if we add these requests and limits. In addition, stability is improved, and the stability of the system and the cluster in general, and quality of service policies are applied accordingly within the Kubernetes. Next step, we will go a step further, adding limit ranges and resource quotas. Why? Because users, in a nutshell, as you all know, cannot be trusted. So we have these limit ranges, and these limit ranges enforce limits and requests across the namespace. And they are also able or help us set default resource requests and limits. And in addition, they enforce ratio between the default limits and requests, and they are applied per namespace. And on the other hand, we have resource quotas, and with those quotas, you can basically control how much resources your namespace can use, so we can restrict the amount of available memory and CPU. And both of these resources do not allow application to start if something is off, and they are as well applied per namespace. Moving on with the step, applying light switch ops. So what's a light switch ops? Basically, it's turning off resources when you don't use them. And this is quite simple step, but often not taken. And it can lead to a big reduction of resource usage and power consumption, and with that, emissions. We can perform a scream test. So basically, we can turn off something and wait for somebody to scream at us to let us know that we need to turn it back on. Some examples could be turning the development and test environment during non-working hours, or mainly probably running smaller instances or number of replicas when the application is not used. And tools that can help us here can be KubeGreen, which is a simple tool, quite enough, really easy to use, and KEDA. KEDA I will mention in the next slide. So moving on to some advanced resource scaling, we will mention here KEDA. And KEDA is Kubernetes Event-Driven Autoscaler, and it enables workloads auto-scaling based on some real-world events. It improves resource consumption and reduces emissions quite big time. It can scale deployments, stateful sets, and job resources, but besides that, it can scale also some of your custom resource definitions. It works alongside horizontal pod autoscaler. It is a bit more advanced, so it's fine-grained, and also it can scale to 0, which HPA cannot do. As I said, it can scale workloads based on external events and possible use cases. You can run batch jobs when energy is greener. So what does that mean? Basically, when energy in the system is coming from the renewable sources, and or scale up and down resources based on carbon intensity. So whenever we get our electricity from something that is not that clean, such as hard coal, like in Serbia, unfortunately, you can scale up and down resources based on that. Here is how KEDA architecture looks like, and I would just want us to focus here on external trigger source. And this external trigger source can be anything. So basically, you can use Kepler metric, you can use HTTP response to modify and scale your application. But also, you can use something called Green API. And these Green APIs are basically APIs that provide you power consumption data throughout the day. And this API, one of these APIs is called electricity maps. And the next slide, you can see this API in practice. This is an application from electricity maps that shows you cleanliness or how clean is your energy. As you can see here, Serbia is here with brown. That means like quite big carbon intensity. So what I did, I took the data from this API and added some scaling. You will see a demo in the next slide. And sorry, but I have only screenshots here, so trust me, it worked. So on the left side, we see K9s, which is a simple text user interface that shows pods within a Kubernetes cluster. And on the bottom side, you can see the logs. So what I did, I created a sample app that fetches the carbon intensity data from the API that I mentioned before. And it reacts, or it tells KEDA what to do about it. So here we have carbon intensity of 331 grams of CO2 per kilowatt hour. I added a configuration for the application to scale whenever this carbon intensity gets updated to below 200 grams. And I've used German zone, so Germany as a country, because it doesn't fluctuate a lot in Serbia. It's big and it stays big, so yeah. And on the right side, you can see how that looks in practice. With lower carbon intensity, you see three scales, three replicas of the deployment. In some of the next slides, you will see a QR code that will guide you to the repo for the application, so you can explore it yourself. I prepared both application code and deployment code, so you can test it out on your locally K3s cluster or whatnot. Moving on. Now, covering the steps to reduce emissions outside the cluster. So, OK, we fixed the internals. Now we make sure that our balloon is covered, and we can add another balloon if we actually need it. So what does that mean? Well, basically, less nodes means less energy, means less emissions. And this can be applied to different cloud providers. Besides emission, we can reduce costs. As Ricardo mentioned it earlier, this could be one of our major selling points for adding sustainability into our development life cycle. We can reduce costs with it by quite a lot. Correct cluster workloads resource usage is a requirement. So what I mentioned before, we need to first figure out the things inside the cluster and then moving on to the outside. And here we have our main objective here is to scale nodes up or down when needed. And we can differentiate here between reactive and proactive scaling. So what's reactive scaling? One of the tools that we can use for the reactive scaling is Cluster Autoscaler. And it's Kubernetes native tool. And it's adding and removing nodes configured per node groups. And it's available for multiple cloud providers, especially the main ones. And it does mainly reactive scaling. So in case of increased usage, it will scale up. And in case of the decreased usage, it will scale down based on the configuration. And on the other hand, we have another tool called Carpenter. And this tool is doing auto-provisioning of nodes based on node pool configurations. And it's doing mainly proactive scaling. It works best with AWS because they developed it, but they also support other main cloud providers. But to be honest, I haven't seen the documentation about other cloud providers other than AWS. And yeah, it's doing proactive scaling. So instead of spinning multiple instances of similar nodes, it can take this and spin up one bigger node instead of multiple smaller ones. So to summarize, first, we need to measure our consumption. So it will help putting things into perspective. How much energy do we consume? How much carbon do we emit? Next, we need to first optimize inside the cluster so we can figure out our workloads, start simple, and then, if needed, we can optimize a bit more advanced. Then right-size Kubernetes nodes. So they're the most important. Kubernetes nodes are most important link in the chain, and their size determines how much resources do we consume. And right-sizing is one of the most important things, but optimizing inside the cluster is a requirement. And last but not the least, applying the light switch ops. So it's the simple tactic to start with, and it's basically turning the switch on or off when not used. Feel free to turn off your dev instances during the weekend, for example. That can save your decrease your emissions and save your costs, definitely. So this is a empty title slide for your questions. If you have any, feel free to ask raise your hand. Thank you. Thank you. Let me quickly check if there are any questions from the application. I don't see any. Yeah, I think that's it. If you want to find out more, yeah?
Right. First of all,
yeah, okay.
show up the QR code. I will do the Vanna White, if you're old enough to know what this is.
This QR code links to the repository
Fantastic.
of the application and the deployment, so you can feel free to check it out. If you want, we can go through it quickly, but if not, that's totally fine.
There is a question. I have been told there is a question.
Yeah?
I can't see. Can you shout it? Oh, you have a microphone. Oh, that's fun.
Well,
Hi.
thank you for the presentation. Which cloud provider is the greenest?
Which cloud provider? Okay. Every cloud provider is green on their own way. Just kidding. I think Azure, by far. GCP is next. Maybe GCP as well. But Azure and GCP are quite on par with one another. GCP, for example, has really good and efficient data centers. There is this metric, power usage efficiency. And Google data centers are quite low on this power usage effectiveness. They send, so this metric tells you how efficient the data center is, so how much energy goes into the data center and how much energy is used by servers and the hardware that is actually in the operations. And the number close to 1, it's better. And GCP data centers are really, really close to 1. So yeah, I would say it's between Azure and GCP.
I have a marketing question for you. How do you convince your boss's boss to get on track with this? How do you market this product?
I would say main selling point is cost reduction. And that's, from my perspective, that can be done with this. So we approach it from the cost reduction, and besides, okay, we optimize additionally, and with this, we also decrease our emissions.
Piece of advice, folks. Use the money, always. But second piece of advice, if you want people to make that decision and not think too hard, propose it on a Friday. They are more likely to accept, okay? Because nobody has their mind on work on Fridays. Well, thank you very much for this, Marjan.
Thank you.
And if you have more questions, do not hesitate to find him. He's easily, not really, you look like a typical developer. But thank you very much.
Thanks,
and
everyone.
we have a break now.
Thanks for having me.